Here is a fourth equilibrium problem. In this case, they don't want the equilibrium constant. They give it to you. But rather, they'd like the equilibrium concentrations that result from the reaction. And intuitively, that makes sense. If you know it has a lousy equilibrium constant, which it doesn't, it has a pretty high equilibrium constant, you should know that the reaction is going to go pretty far, but not to completion. And it should be quantitative because you have an exact number. So intuitively, you should be able to figure out the concentrations of everything at equilibrium. But how you do that, since they want all three of them, three unknowns for a problem, oftentimes seemingly insoluble, unsolvable, but there's enough data in here to solve it. So let's go ahead and do it. Now there's an easy way and a nice tables method. I tried to point out that sometimes the easy way doesn't really work, and this is an example where the easy way is, boy, maybe you could do it that way. I'll show you both ways and you make your own decision. The question says the equilibrium constant is very high, 55.64, for this synthesis of hydriodic acid. I'm initially noticing that I know I'm going to have to set up an equilibrium constant expression. I know that this will become an exponent here. Nothing gets removed, so good. I'll be able to set it up. They give you the temperature, which as long as it's constant, and it is. See how it's still 425. I ignore it. That just means my data will work because the temperature's not changing. And they give you the initial concentration. No, they don't. They tell you they have 1 mole of it. Hey, concentration is in moles per liter. Are placed in a point. Oh, okay. Moles per liter. 1 mole and half a liter. 1 divided by 0.5. That's 2 molar. Iodine, exact same. That's 2 molar. So don't be fooled by that. They're just giving you enough data to calculate the concentrations. And then they want to find out all three. Wow, should I just go and set up a nice table? Probably, but here's how you can do it without it. We can write the equilibrium constant expression. K, which they give you, is equal to this squared, notice the 2, divided by each of those. And they don't give you any of these things, so they do give you the initial concentrations. So for each of these reactants, which are on the bottom, since the coefficients are 1, they will go down by a value of x. For this one, we don't know what it is, but it's going to go twice as much of a change, since there's 2 of these that form for each one of the reactants that goes away. And so it'll be double, and we still have that exponent there. And so that is a generic setup. Is that enough to solve for x? Punch it in and you'll actually see it is. In this particular case, which is unique to this problem, these are the exact same volumes. So this is 2 minus x squared. If we solve it, and I'm going to show you how to solve that in detail. This was a lot of steps, but there's the value for x. Aha, great. That's not the concentration of each. Now we got to think for a second. X is equal to 1.58. We put it in right there. This is the concentration in those brackets. Once we do that, we don't care about the square because we want to know the concentration of each. So whatever 2x is that. 2 minus x is the other one. 2 minus x is the third one. And if x is 1.58, 2 times 1.58, the concentration of the hydriodic acid is twice x. That should be 1.58, and that's 3.16 molar. The other ones each went down by that amount. They went down to 0.42 molar. We have answered the question. If you can do it using that way, more power to you. But most people would do it by the ice table method, which lays it out a little cleaner. Note that the molarities are twice the number of moles because it's 1 mole divided by 0.5 liters. That's the concentration in moles per liter, which is 2 for both of the reactants initially. How much does it change? Well, it's going to go up by a value of 2x since 2 of these form, and it'll go down by a value of x. Each one of those each go away stoichiometrically. And therefore, the change at equilibrium, this is 2x, and each of these are 2 minus x. Notice we just calculated the exact same thing that we did in our head there. Plug it in. Now here's how you can solve, in case you're worried about solving this mathematically. Probably the easiest thing to do is take the square root of both sides. I can take the square root of this, it'll be a little over 7. I can take the square root of that, just remove the squared. I can take the square root of that, remove the squared. And that simplifies it a lot. Now cross multiply. Carry that through. And you'll find we can now do a little subtracting. Now we just divide x equals 14.9 divided by 9.459. We're dividing both sides here by 9.459. Same value, looks good. Once again, plug them in. 2 minus x is 0.42. 2 minus x is 0.42. 2 times x is 3.16. And see how it's a little cleaner throwing them both in there, and that's a little bit why some people like these ice tables. Same value either way, and we're done with the problem. This is a fourth example of an equilibrium problem that uses an ice table.